Here are two classes of points, and they sit apart cleanly. Gold on one side, blue on the other. Our job is to draw a boundary between them. And here is the awkward truth. Infinitely many straight lines separate them perfectly. This one, this one, this one. Every one of them gets the training points completely right. So which line should we trust? The support vector machine gives a beautiful answer. Don't just separate them. Separate them by the widest possible empty street. Picture rolling out the fattest band you can between the two classes, without touching a single point. The line running down its middle is the one we keep. Let's write that boundary down. In any number of dimensions, the boundary is a flat hyperplane, and it has one clean equation. W dot x plus b equals 0, three pieces. X is the feature vector, the point we're looking at. W is the weight vector, and geometrically it's the direction perpendicular to the plane. It's normal. And B is the bias, which slides the whole plane back and forth. Once we have the plane, classifying is effortless. Plug a point in and just read the sign of W dot x plus b. This tells us the two classes are +1 and -1, a choice that will pay off in a moment. If the result is positive, the point sits on the gold side. Call it +1. If it's negative, the blue side, -1. The plane itself, where the expression is exactly 0, is the fence between them. Let's name the three lines that matter. The gold line in the middle is the decision boundary, where W dot x plus b is 0. On either side, we draw two parallel margin lines, one where the expression equals +1, hugging the gold class, and one where it equals -1, hugging the blue class. The empty strip between them is the margin, and the weight vector W points straight across the street, perpendicular to all three lines. It sets the direction of the boundary. The margin lines are just parallel copies, one unit of the score to each side. Now let's measure that street exactly. The distance from any point to the plane is the score. W dot x plus b in size divided by the length of W. That division by the norm of W is what turns a raw score into a true geometric distance. Take a point sitting right on the +1 margin line. There the numerator is exactly 1, so its distance to the boundary is 1 over the norm of W. A point on the -1 line? By the very same reasoning, also 1 over the norm of W. The full margin is the two half-widths added together, 1 over the norm of W plus 1 over the norm of W, which is simply 2 over the norm of W. There is the headline formula. The margin equals to divided by the length of the weight vector. And this flips the whole problem into something we can optimize. Since the top of that fraction is fixed at 2, making the margin as wide as possible is exactly the same as making the length of W as small as possible. Widest street, smallest weight vector. Two ways of saying one thing. Now the idea that gives these machines their name. Here is the boundary, and it's two margin lines, with the points scattered on both sides. Look at the points that actually touch the margin lines. One gold, one blue, sitting right on the edge of the street. These are the support vectors. They satisfy y times the score equals exactly 1. And here is the surprising part. These few points alone pin down the entire boundary. Every other point sits comfortably outside the margin, with its score greater than 1, and it has no say at all. Delete one of those faraway points, and the boundary does not move a hair. Let's put numbers on all of this. Suppose our trained machine has weight vector 3, 4, and bias -12. First question. How wide is its margin? The length of W is the square root of 3 squared plus 4 squared, square root of 9 plus 16, which is the square root of 25, a tidy 5. So the margin is 2 over 5, exactly 0.4. That's the full width of the street. Next, let's classify a point. Take x equals 4, 2. Plug it in. 3 times 4 plus 4 times 2 minus 12. That's 12 plus 8 minus 12, which is 8. Positive. So this point is classified +1, the gold class. Try another, x equals 1, 1, 3 plus 4 minus 12 is -5, negative. So it lands in the blue class, -1. Finally, let's spot a support vector. The point 3, 1 from the gold class gives a score of 9 plus 4 minus 12, exactly +1. So y times the score is +1 times +1, which is 1. It sits right on the margin line, a genuine support vector, and a blue one, the point 1, 2. Its score is 3 plus 8 minus 12, exactly -1. Times its label -1, that's 1 again. Both of these points touch the margin, and between them, they hold the whole boundary in place. So far, we demanded a perfectly clean split. But real data is messy. Often no straight line separates the classes without error. So we soften the rule. We introduce a slack variable, 11. For each point, a small allowance to break the margin. The hard rule said the score must be at least 1. The soft rule relaxes it. The score must be at least 1 minus 11, where 11 is never negative. The size of 11 tells the story. 0 means the point is safely on the right side, outside the margin. Between 0 and 1 means it has slipped inside the street, but is still correctly classified. And 1 or more means it has crossed all the way over, a genuine misclassification. Now the machine juggles two wishes at once. Keep the weight vector small for a wide margin, and keep the total slack small for few violations. A single knob, capital C, sets the exchange rate between them. Turn C up high, and the machine punishes every violation fiercely. It shrinks the margin to fit the training points and risks overfitting. Turn C down low, and it tolerates some slack for a wider, smoother boundary that often generalizes better. Here's the case that breaks everything so far. The gold class sits in a little cluster at the center, and the blue class forms a ring around it. No straight line on this plane can ever separate an inside from an outside. Try to draw one, and it always cuts the ring. Some blue points fall on the gold side, no matter how you tilt it. A line is simply the wrong shape for this data. So here is the trick. Add a dimension. We lift every point off the flat plane into 3 dimensions, giving each one a new height, z, equal to x squared plus y squared. Its squared distance from the center. Points near the middle rise only a little. Points on the ring shoot up high. Watch what happens in the lifted space. The gold cluster stays low, hugging the floor. The blue ring lifts into a ball, floating well above it. Suddenly the two classes are stacked, one low, one high. And now a plain flat plane, sliding in at height 3, separates them perfectly. Every gold point below it, every blue point above. In this richer space, a linear boundary does the job the line never could. And here is the payoff. Project that flat plane back down onto the original plane, and the cut it makes. The set where x squared plus y squared equals 3 is a perfect circle. A straight plane upstairs becomes a curved circular boundary downstairs, wrapping the gold cluster exactly. The genius of the kernel trick is that we never actually build those lifted coordinates, which could be enormous. A kernel function computes the dot product in the feature space directly from the original points alone. Popular choices are the polynomial kernel and the radial basis function kernel. The boundary is linear up there and curved down here, and we never leave the ground. Your turn. A trained support vector machine has weight vector 6, 8. What is the width of its margin? Pause the video, work it out with the formula, and I'll wait right here. Here's the walkthrough. The length of W is the square root of 6 squared plus 8 squared, square root of 36 plus 64, which is the square root of 100, exactly 10. So the margin is to over 10, which is 0.2. Notice, the bigger the weight vector, the narrower the street. If you found 0.2, you've truly got the geometry of this machine. Trap 1. cranking C to the maximum. It feels like demanding accuracy, but a huge C shrinks the margin around every noisy point and overfits. The sweet spot for C is chosen by validation, not by turning it up as far as it goes. Trap 2, forgetting to scale. Because the margin is built from distances, a feature measured in thousands will swamp one measured in fractions. Always standardize your features before training, or the boundary is warped by units alone. Trap 3. Thinking a soft margin just ignores mistakes. It doesn't. Every violation costs, through its slack variable in the objective. The errors are controlled and paid for, never waved away for free. And trap 4. Reaching for a fancy kernel blindly. The kernel decides the shape of the boundary. A linear one for straight splits, an RBF for blobs and rings. Pick the wrong one, and you force the wrong geometry onto your data. Let's lock it all in. A support vector machine classifies by the sign of w.x plus b, a flat hyperplane splitting the classes. But of all the planes that could work, it picks the one with the widest margin to over the norm of w, which means simply making the weight vector as small as possible. That boundary rests entirely on a handful of support vectors, the points touching the margin where y times the score equals 1. The rest don't matter. And when a straight boundary won't do, soft margins let a few points slip, while kernels lift the data into a richer space where a plane separates it. A circle drawn without ever leaving the page. That is the support vector machine.